And there's two types of notations. First, we have what are called prime notations. And as you've seen thus far in the course, prime notations would be y prime, which would be the first derivative. Higher order derivatives would be derivatives such as y double prime, which is the second derivative, y triple prime, which is the third derivative, and so on. There are also another type of prime notations, which are f prime of x, which again is the first derivative. We have f double prime of x, f triple prime of x, and so on. There are also another type of notations, which are Leibniz notations. And in these type of notations, we use the dy dx. That would refer to the first derivative. We have the second derivative as d squared y over dx squared. And the third derivative would be written as d cubed y over dx cubed, and so on. So let's take a look at an example. So in this example, we're asked to find the first and second derivative for our function, which is 4x minus 3 divided by x. Now from algebra, there is a rule called divide by a binomial. Well, excuse me, divide by a binomial. And binomial is just simply a binomial with one term. You have a plus b over c. So notice I have a monomial in the denominator. Then you can treat the denominator as a denominator for every term in the numerator. So I can rewrite this as a over c plus b over c. And I'm going to do the same thing here. I'm going to treat x as a denominator for every term in the numerator. So this equals to 4x over x minus 3 over x. I can simplify that a little bit further. I can write this as, my x's will cancel. I can write this as 4 minus 3 times x to the negative first power. I can rewrite negative 3 over x as negative 3 times x to the negative first power using something called the negative exponent rule. And it states that a to the negative n power is equal to 1 over a to the positive n power. Hey, just reviewing some facts from algebra. So now we're going to take our f of x equation, which we've rewritten as 4 minus 3 times x to the negative first power. We're going to find the derivative. So remember that the derivative for any constant is 0. Next, we're going to use a power rule. Right? So we're going to treat negative 1 as a multiplier. Right? So negative 1 times a negative is a positive. And then we're going to subtract 1 from our exponent. So 3 becomes positive. X raised to the negative 1 minus negative 1 is x to the negative second power. So we can express the derivative as 3 times x to the negative second power, or we Now we're going to find the second derivative. So I want to keep my exponent as a -2. Therefore, I can more easily use the power rule. So finding the second derivative, I'm going to treat -2 as a multiplier. I'm going to subtract 1 from my power. So -2 times 3 is -6. X raised to the -2 minus 1 is the -3rd power. And I could write that as -6 over x cubed. All right, so either way you want to write that first or second derivative. Now we're going to take a look at a radical. So in this example, we have f of x is equal to 12 times the square root of x, and we're actually finding the first and the second derivative. We can rewrite a power as a radical and a radical as a power. For example, and here again I'm just using one of the rules from algebra. We have the formula to convert a radical to a rational exponent. So just keep in mind that rational just means fraction. So we can rewrite a radical as a fractional exponent. And here is the formula. We have the square root, but I'm going to replace that square with m. So m is your index. All radicals have an index. If you don't see an index, it's understood to be a square root. But we do have other roots, square roots, cube roots, and so on. And whatever is underneath our radical is called our radicand. Right? And all radicands carry some type of exponent. In order to rewrite this radical as a rational exponent, the base of my radicand is going to be the base for my rational expression. And then I'm simply going to put the power over the index. So this actually gives us a formula. So let's take a look at an example. We're asked to rewrite the radical as a rational exponent. All right, so we have the square root of x. So keep in mind this square root of x has an index, which is 2. It also, the radicand has a power, which is 1. So the base of our radicand is the base of our rational exponent. So that base is x. And then we're going to simply take x and we're going to raise that to the power over the exponent. Therefore, we can rewrite the square root of x as x to the 1/2 power. So I'm going to rewrite 12 times the square root of x as 12 times x to the 1/2 power. And now I'm going to apply the power rule. I'm going to treat 1/2 as a multiplier, and I'm going to subtract 1 from the exponent. So notice I'm just simply writing 1 as a denominator of 2. Therefore, I can simply subtract these fractions, because remember, in order to subtract fractions, you must have a common or like denominator. So once we take the first derivative, we have half of 12 is 6 times x, and if we subtract 1/2 minus 2 over 2, in order to subtract fractions, we're going to keep the like denominator, which is 2. We're going to combine our numerators. 1 minus 2 is -1. So we have 6 times x raised to the -1/2 power. We're going to repeat that process on finding the second derivative. I'm just going to write 6x to the 1/2 here just to give me a little bit more room. I'm going to treat -1/2. We must keep the sign. I'm going to write that as a multiplier. I'm going to subtract 1. -1/2 of 6 is -3. And if we subtract -1/2 minus -2/2, we get x to the -3/2. We'll next take a look at another example. We have find and interpret f prime of -1 and f double prime of -1. And we're given that f of x is equal to 3x squared minus 3x minus 1. In order to find f prime of -1, first we must find f prime of x. So I'm simply going to use a power rule. So the derivative for 3x squared is 6x. The derivative of -3x is -3. And the derivative of any constant is 0. So now in order to find f prime of -1, I'm simply going to substitute -1 for x. So that's 6 times x, which is -1, minus 3. 6 times -1 is -6. And -6 minus 3 is -9. Since our derivative is negative, this means that our function is decreasing. Every time you have a negative value for your derivative, whether it be a first derivative, second derivative, no matter what derivative, if that quantity is negative, then the value is decreasing. Now we're going to find f double prime of -1. So first we'll start off by finding f double prime of x. So if we go back to our f of x equation, I'm going to take the derivative for 6x, which is going to give me 6. The derivative of any constant is 0. Therefore, the second derivative of x is 6. Now we're going to find f double prime of -1. So notice there is no x variable to substitute into our second derivative. So the value of f double prime of -1 is simply 6. Since the value of our derivative is positive, that means that our function is increasing. Sometimes you may see negative and positive written in an interval notation. So let's just say anything that's positive is greater than 0. Therefore, the second derivative is greater than 0. That means the second derivative is increasing. Any value that is negative is less than 0. So for our first derivative, it's less than zero. So less than zero means negative, and decreasing greater than zero means positive and increasing.